In this second video about solubility, we're going to take a look at what can affect the solubility of an ionic compound in water. And so we're going to take a look again at this situation with calcium fluoride dissolving in water. When we looked this up, or we calculated this in the previous video, we found that the molar solubility for calcium fluoride was 2.13 times 10 to the negative 4. And through the idea of just Le Chatelier's principle and the common ion effect, if we add or if we dissolve calcium fluoride into a solution that already has some calcium or already has some fluoride in it, we would expect that the equilibrium will shift to the left to where the undissociated or undissolved calcium fluoride is, and that the solubility would actually decrease. So a common ion will decrease the solubility. This sample exercise here just asks us to actually calculate that with actual numbers. So it says calculate the molar solubility of calcium fluoride at 25 degrees Celsius in a solution that is 0.010 molar calcium nitrate and 0.010 molar sodium fluoride. So if I just, choose A, the KSP, of course, would be equal to the concentration of the calcium ion to the concentrate times the concentration of the fluoride ion squared. And the KSP from the previous example is 3.9 times 10 to the negative 11. The calcium ion is 0.010. And then we would solve for the fluoride ion. When I solve for the fluoride ion, I get... Then, of course, we would need to divide by 0.01 and then take the square root of that answer to finally get that the concentration of the F minus at equilibrium would be 6.2 times 10 to the negative 5. But that actually isn't the molar solubility of calcium fluoride, because remember, according to the balanced chemical equation, that you'll have 2 moles, I'll do it out here, right, would be Ca2 plus 2F minus. So if I were to do like a little bit of stoichiometry here, that it would actually be half that. So the molar solubility of calcium fluoride in a solution that is already 0.010 molar in calcium would just be 3.1 times 10 to the negative 5 molarity. And that is less than the original molar solubility of calcium fluoride, that 2.13 times 10 to the negative 4 number. And if I look at B over here, right, it's already starting out with some fluoride ion in it. Same exact thing, 3.9 times 10 to the negative 11 equals the concentration of the calcium ion. I don't know this time, but I do know the fluoride ion is 0.010 squared. Solving for the calcium ion, I get 3.9 times 10 to the negative 7 molarity. And since calcium ion and calcium fluoride have the same coefficient, then that is the molar solubility of the calcium fluoride in a solution that is already 0.010 molar in fluoride ion. So we can see both of these numbers are lower than they would be if we dissolved it in pure water. Now, although we're not often dissolving an ionic compound in something that already has that ion in it, if the ionic compound that we are dissolving has certain ions, the pH of that solution may really affect the solubility of it. So we're going to be looking at solubility and pH here. And there's 2 circumstances that we're going to be looking at. If the anion is basic, and the cation is acidic. So remember, anion is the negative guy. What the heck does that mean if the anion is basic? So what that means is if it has a basic anion, think about all of the acids that we know. We know some acids are strong and some acids are weak. What we are essentially saying is that any negative ion that if you put an H with it, it would not equal a strong acid, but it would equal a weak acid. So anything that's not Cl minus, Br minus, all those guys are the anions associated with strong acids. The reason why this works is because then that ion will react with the hydrogen in the sample, and that will essentially pull the equilibrium to the right, like think in a Le Chatelier's principle type way. So if I were to, have this, and then I were to make it more acidic, right? That would mean adding lots of H+. What would happen is the H+ and the F- would come together. The F- would react with the H+, and it would form HF. Remember, what makes the difference between a strong acid and a weak acid is that a weak acid does not fully dissociate in water. So therefore, it will actually consume some of the F- and it will become more soluble in a more acidic solution. So if the substance has a basic anion, it will be more soluble in a more acidic solution because the hydrogen will react with that. Think of if we were looking at this instead of PbF2, if it was PbCl2. Right? Would the H+ react with the Cl-? No, because HCl is a strong acid and that's always completely dissociated. So here's a graphic picture of what we were just talking about, right? Here's PbF2, and you can see it's just barely soluble. There's very little of the fluoride and the lead floating around in solution. But if I add H+, what that H+ is going to do is it's going to react with those F- ions, and so therefore it will pull the reaction through Le Chatelier's principle, pull the reaction to the right. But if I'm using PbI2 and I add H+, HI is not going to form because HI is a strong acid. So it all has to do with whether the anion is associated with a strong acid or weak acid. And since you've memorized the 7 strong acids, you know every anion that is not associated with a strong acid we could consider weak. And this is sort of the other scenario. If it has an acidic cation, so what that means is that its positive ion, if you add OH-, does not make a strong base. It will be more soluble in a basic solution for the same reason. The OH- will react with that positive ion. It will pull the equilibrium to the right, and it will become more soluble in that basic solution. So here's a list of these 4. It says, which of these substances is more soluble in an acidic solution than in a basic solution? So what does that mean if we're talking about in an acidic solution? That was like that first example that we saw. So we want to be looking for the negative ion, and it's not associated with a strong acid. That's what we're looking for. So what is the negative ion on here? OH-. So then is HOH a strong acid? No. So this guy will be more acidic in more soluble in an acidic solution. What about CO3 2-? Is H2CO3 a strong acid? No, it's a weak acid. So H2CO3 will form. It will be more soluble in an acidic solution. What about this guy? Is F-? Will HF form? Yep. It's not a strong acid. But for Cl-, Cl- will not form a compound with HCl. That's completely soluble, so those two will never come together, and it will not be affected by pH. Second practice exercise here is which of the following actions will increase the solubility of AgBr in water? So you got to think about like what might react, right? Increasing the pH. If this means increasing the pH, what does that really mean? That means adding some OH-. So what would happen? Well, what's the positive ion? Ag. Will that react with OH-? Yeah, right? And therefore it will increase the solubility. So this one, because it will make AgOH. So this one will work. What about decreasing the pH? That means adding H+. That's a positive ion. So will H+ plus Br-? Nope. That's not going to affect the solubility because HBr is a strong acid. What about adding NaBr? That would mean Br, that's the common ion. And we know common ions decrease solubility. Adding NaNO3, none of these ions have anything to do with AgBr. They're both spectator ions. The Na plus isn't going to react with the Br minus because Na plus is always a spectator ion. The NO3 minus isn't going to act with the Ag plus because NO3 minus is always a spectator ion. So that's going to have no effect on the equilibrium. And then E is none of the above. So we already figured out that. Of course, the answer is the first one, A.